Greetings to all, welcome to the channel Simtech05. In today's video, we will discuss about ductile damage criteria and its damage evolution parameters. In damage analysis, selection of damage parameters, material and mass play a very crucial role, and all these are sensitive for the output. So in few sequential videos, we will talk about the damage parameter and damage criteria. Later on, we may discuss about the mesh sensitivity on the damage analysis. So here you can see the ASTM standard tensile test specimen. Once the specimen meet the damage criteria, the element from the respective place start deleting, or we can say the damage start. So in few slides, we will talk about those parameters, importance of those parameters. We will little bit see the theory behind the damage evolution. This video is especially concentrated on damage evolution parameter and how we can choose such parameter for the particular component. Many times it happen like in the simulation, we define the proper boundary conditions and material parameter, but still we not get the damage. Okay, experimentally we may get damage, but in the simulation we may not get damage. The reason behind this error is damage evolution parameter. Let me check on the laser point. So as we can see in the first case, here the same material and boundary condition apply. In all three cases, same material and boundary conditions applied. But in this case, we can see instead of damage from the particular location, it start distorting randomly from these locations. As I mentioned, we have same material parameter and same boundary condition and same meshing. Only the difference of the damage parameter. In the second case, damage take place, or you can say element start deleting or removing from the crack location, but still it is not appropriate. As you can see, the crack nucleation is random on the particular locations, first, second and third location. But in third case, once we define the proper damage evolution parameter, we will get the proper behavior of the crack component, or we can say element delete properly with respect to the damage parameters. See, there we have two things. One is damage modeling, damage material model, and second is damage evolution parameter. We will talk on that. So here we discussed about the damage evolution parameter, not about the damage material modeling. We have same material model, same damage material model for the all three cases, but different damage evolution parameter. So there we have some frequently asked question. Let's discuss on that first. The first question, sometime element deletion occur and sometime element deletion not occur, or element deletion not take place. What is the reason behind that? Personally, what I understood, there we have two major things. One is the governing parameter and other one is observing parameter. We will talk later about the observing parameter, but in the governing parameter, especially damage evolution parameters play very important role, and in damage evolution parameter we have to define two things: damage parameter and displacement at failure. The second important point, second important governing parameter is your fracture strain, and third is boundary conditions, especially the applied load. If these three parameters are correct in our simulation, then there are high chances of good results. And the observation parameter is our equivalent plastic strain. Sometime even if my simulation is correct, I mean to say the parameters of the simulation is correct, but due to some reason the damage is not occurring, It should occur as per experiment, but it is not occurring within the simulation. Then we can observe the reason with help of plastic strain, equivalent plastic strain. That's why I'm saying this parameter as a observation parameter. Okay, apart from that, we must check on the status within the software. If you are aware to the damage type of analysis or element deletion type of analysis, you must know the status. If you don't know, in subsequent slides or subsequent videos, I will let you know from where you can check on these status options and deletion options from the mass module. Do not worry about those. These are the another parameter which must check on. So now question is, what should be the displacement at failure? See, here we have two damage evolution parameter. First is damage parameter and second is displacement at failure. Damage parameter is fixed. At 2 point it is fixed. At the beginning it is 0, at the end it will be 1. But what should be the displacement at failure? What value we have to feed? That is the major question here. Fracture strain is depend on the material. It's a material property. Boundary conditions are our given conditions, but those should be accurate. Okay, that's why I mentioned here governing parameter. These parameter you may have, but the problematic parameter is displacement at failure. So the what value we have to feed. Of course, we will discuss this particular point, but before that, let's discuss a little bit about the damage. So what is damage? In simple word, if I want to explain, it's a progressive degradation of the material stiffness, and that degradation in the material stiffness lead the failure. Here you can see one example. The material stiffness is start degrading and at the end the failure take place, a continuous failure take place. The stiffness degradation we can see here, we can observe here with respect to the number of cycles. As number of cycle increases, the stiffness of the material, stiffness of the element, in FEA we can say element, is reducing, and ultimately the particular region in the material, or we can say the elements, particular elements in the finite element analysis not able to sustain any of load, it's mean those stiffness is completely zero, then those elements are subject to deletion. We are not going to switch directly on the damage analysis. We will talk from the basic. See, for the linear analysis, what parameter we have to define? Material parameter. We have to define only the elastic limit with the Young's modulus. Here we can see. If you want to perform such non-linear analysis, here I am talking about the material non-linearity, not on the contact and geometric non-linearity. So if you want to perform material non-linearity, along with this Young's modulus and Poisson's ratio, what we need? We need the plastic parameter. So along with this elastic limit, what we need? We need the plastic parameter. Okay, here I consider only two plastic point. The 100 is the yield point, and then this is the ultimate stress and strain respectively. This is the classical nonlinear theory. But apart from that, we have different plastic material models. For metals, mostly we prefer mechanical plasticity and plastic material. In that plastic material itself, we have different type of strain hardening condition like isotropic, kinematic, Johnson-Cook, etc. And we have sub options like rate dependent, cyclic loading, etc. For most of the metals, this plasticity is sufficient enough. But if we go for the non-metals like concrete, we have especially here concrete damage plasticity. Apart from, we have Docker pressure condition for civil engineering, more Coulomb plasticity and soft rock plasticity, etc. For the mechanical engineers, the classical plasticity, cast iron plasticity, and sometimes porous metal plasticity is important. Of course, the creep, swelling and viscous is common for both civil and mechanical engineering, and those are the completely different era. Okay, that's enough. Up to that we seen for the elastic material, or we can say for the linear material, we need to define only elastic limit. For the plasticity along with the Young's modulus and Poisson's ratio, we have to define the plastic parameter, and this is nothing but classical metal plasticity. What if we want to involve the necking and damage within the simulation? That's a really very problematic. We will see why it is problematic. So for that we need to define the damage criteria, that may be ductile damage criteria for the ductile material, and we have to define two things: damage evolution parameter and damage material property, along with choice of element removal options. This is nothing but if stiffness degrade up to certain limit, software will remove those elements. Here we can see the true stress strain curve, and to define the damage we must go beyond the ultimate tensile strength point. So we will discuss this in brief in subsequent slides, so not worry about that. Okay, so for necking and damage, or we can say to model such necking and damage, what we need? We need the material with damage property and then damage evolution parameter or damage evolution response. So we have few material in Abaqus, those material allow the ductile damage criteria. Especially for the fracture of metals, we have ductile criteria and shear criteria. And for necking instability, especially in the sheet metals, we have forming limit diagram FLD curves. This S is nothing but representing the stress forming limit stress diagram. MS is the name of any researcher prefixed by FLD, and another criteria we have MK criteria. This FLD, or we can say forming limit diagram, is very important if you are working on the sheet metals. These material model is specially designed for the sheet metals. Apart from, you can utilize here the ductile criteria and shear criteria along with the famous Johnson-Cook damage criteria. So basically these type of damage criteria we have, this type of damage material we have within the Abaqus for the metals. Okay, one more thing, fracture mechanics. That is the completely different thing from the damage modeling. Means fracture and damage ultimately the similar kind of thing, but FEA point of view, their theory, their implementation is completely different. So we are not going to talk about the fracture mechanics here, we are going to talk about the ductile damage criteria especially, or we can say damage criteria. So as per our definition of the material and the damage evolution parameter, once material meet the damage initiation criteria, or we can say material satisfy the damage initiation criteria, the material stiffness is going to be reduced. And how material stiffness going to be degrade? It will be degrade according to the specified damage evolution law. Okay. So again and again I am repeating, there are two things. One is the damage material and second is damage evolution law or damage parameters. Let me show in Abaqus itself. So here we have one ASTM component, and let me show the properties. See, this is my material property. Let me double click. Ductile damage parameters like fracture strain, and we can say triaxiality, or if it is rate dependent component or not, density parameter, elastic and plastic parameter. Those are the parameter for the ductile damage material. But this particular parameter, damage evolution, when you double click on that, this is my damage evolution law, or we can say the damage law. Here this value 5 is wrong, okay? Just to show you what will happen if I feed this value randomly, I feeded that value 5. Do not worry about that. If someone say, what happen if I define only this ductile damage parameter in the material, but I am not going to define this damage evolution law or damage law? I can simply delete this. So we don't have now damage evolution law. So what will happen then? Will stiffness of the element still degrade? Will element still delete or not? In one word, no. Software will unable to understand which element it has to be delete, which element's stiffness is going to be degrade. Even if I define the damage material motor, but we don't have damage evolution law, Abaqus will evaluate the parameter only for the output purpose. But Abaqus will not affect the material response. I mean to say, it will not going to degrade the stiffness. So till now we understood we must need both damage material parameters and damage law, or we can say damage evolution law, to delete element at the particular location. The problem is, in classical elastic plastic material, we cannot define the strain softening behavior. So if we cannot include the strain softening behavior, we cannot include the fracture within the material. So what is strain softening in simple term? It's a deterioration of material strength basically. Means even we apply the lower load, lower the stress, the strain going to be increased. Here we can see, here the stress value somewhere at this position, but even we are going to define the lower stress at this point, but still strain is going to be increased, and that is nothing but your strain softening behavior, and this is difficult to define within the material property. Means till that time we was unable to define strain softening behavior within the material. So that was the big problem. In 1976, one scientist, Hilbergs, he defined the energy required to open any crack, that is defined as a GF, and we can see by using this formula. This is nothing but a volumetric energy under stress strain curve. Here you can see the stress term, strain term, and if we consider the volume, then the volume area into length will be considered, but that energy is defined per unit area. So area term will be cancelled out, only the length term will be remains. So this is nothing but energy to open a crack with unit area under the limit of plastic and fracture strain, and here those plastic strain and fracture strains are mentioned. One more important point here, if you observe this particular equation, the effective displacement delta U can be given by L into dE. How? Because the strain is change in length divided by actual length. So the change in length, or we can say the effective plastic displacement du can be given by L into dE, and with respect to that these boundary conditions also will be changed. So this is quite easy term. Just we define the energy required to open the crack, but the crack must have the unit area, and then we convert this dE term into effective displacement term, and as I told you, this du term can be defined as L into dE, and this L is nothing but your characteristic length of the element. This U is our effective plastic displacement and E is the plastic strain. Sometimes this effective plastic displacement is also called displacement at failure, and this parameter we need to define in our damage evolution law. Let me show you See, in the ductile damage, go to the sub options and damage evolution. Displacement at failure, say 0.05 a value, and this is nothing but your displacement at failure or effective plastic displacement that we need to define. So how to calculate this? We don't know what value we have to feed. So for that, we must go with the plastic strain and the characteristic length of the element. So within the simulation, we must know the characteristic length of the element on the particular crack zone. Like here in this case, I know this is my tension specimen as per the ASTM standard. So this will be my fracture zone, damage zone. So within that, I must know the element characteristic length. Okay. And once we know the element characteristic length, we must know the plastic strain as per the material behavior. We can define the effective plastic displacement or displacement at failure value. So for the different type of element, this characteristic length will be given in a different way. Like for the first order element, this will be the minimum of the all edges and the medians. Means whatever edge is minimum or whatever median is minimum will be the characteristic length of the element. For the second order, it will be half of the actual length. Why? Because within the second order, we must have one mid node. So it will be half. For the beam interest element, it's simply length of the element along its axis. For the membrane, the characteristic length is given by as a length of edge within the reference surface. For the axis symmetric element, it is little tricky. See, these are my element. This is axis along which this component is symmetric, and this is the radial direction. So the characteristic length is given by in the RZ plane. So this is my radial plane, radial axis, and this is my Z axis. So this is my RZ plane, and this length will be the characteristic length. For the cohesive element, this will be the thickness of the cohesive element. So we have two component, two object joined with cohesive elements. So this will be the red color thing is nothing but the thickness of the cohesive element. This is only for visual purpose, otherwise this cohesive element thickness is very less. Okay, one more thing, this definition of characteristic length is used because direction in which fracture occurs is not known in advance. We don't know where the fracture is going to be propagate. So therefore, element with the large aspect ratio may have different behavior depending on the direction in which the crack is going to be propagate. So that's why in the crack zone, the large aspect ratio elements are not even recommended, because the mass sensitivity take place here, and it may be very crucial for the crack propagation or element deletion. So try to define very good element within the crack zone, and the aspect ratio is much near about 1. Okay, here we will discuss all about the damage parameter and stiffness degradation. Generally, we seen this graph up to this point only. In this graph, the x-axis is strain, y is stress, and as we can see, this small region, this small zone is my elastic zone. Then we have plastic zone, and this is my plastic strain. How we can calculate? We have to draw a parallel line with respect to this on the ultimate tensile strength. So this is my ultimate tensile strength point, and once we cross the ultimate tensile strength point, the damage region started. So elastic region, plastic region, and this is my damage region. In classical plasticity theory, we have elastic and plastic material properties, but we don't have the properties for the damage region. And in the absence of damage region, after the fracture point, this curve may be propagate likewise. Here, this point is my damage initiation point. From there, from this point, the damage start occurring. Okay, and as I told, this graph will be propagate in the absence of damage, and with presence of damage parameter, this graph will be moved likewise. Okay, apart from the damage material model, we must need to define the damage evolution parameter. Here, the damage evolution parameter at the damage initiation point is 0. I'm saying this D is nothing but your damage parameter. That is 0 at the beginning of the crack, or we can say at the nucleation of the crack. As strain increase, this damage parameter move from 0 to 1. The maximum value of this damage parameter is 1. Up to plastic region, this Young's modulus remains same. Even in the elastic region, even in the plastic region, means there is no change in Young's modulus of the material, or in simple word we can say there is no degradation in the material. But once we reaches to the damage initiation point and we move further, then the Young's modulus of the material start decreasing as per this law, this simple equation 1 minus d into Young's modulus. So here you can see at these 3 points the Young's modulus remain E. Here also up to the plastic point Young's modulus remain E, but here the Young's modulus decreases. So you can see the difference in the slope. This line is representing Young's modulus of the material but within the damage region. And obviously this is fairly low as compared to the original Young's modulus of the material. Another important parameter that we have to observe is the plastic strain and plastic stress, and this is the fracture strain. The fracture strain is always will be greater than the plastic strain. We have to take care of this. So again, the effective plastic displacement or displacement at failure can be defined by L into effective plastic strain that we seen earlier, and we need to define the relationship between these two parameters to define damage evolution law. So in 3 ways we can define this damage evolution parameter or damage evolution law: in tabular form, linear form, and exponential form. Generally we seen this linear form likewise. See the damage evolution law, damage evolution parameters. Type is displacement. There we have two options: displacement and energy. And the softening behavior is linear. In the linear, we need to define only one parameter, displacement at failure. Why? Because the primary point will be always 0. Means when the damage will be 0, look at that, when damage will be 0, the displacement at failure also will be 0. Means there is no failure of the element. No failure of the element. But once the parameter d reaches to 1, so what will be the value of the displacement at failure? Means u. X is representing here displacement at failure and y is representing the damage parameter. So at the beginning they will be 0, 0. At the end, when the d, the damage parameter will be 1, then what should be the value of u? And then this value can be calculated as per this particular formula. So another way is tabular form. Again, the damage parameter will start from 0 and end with the 1. So in between, instead of linear form likewise, you have some different combination. This may you got from the experiment. If you have such combination, you can define. And similarly, instead of those combination, you have exponential factor, you can define that exponential factor. So in this way, we have to define the damage evolution law. These are the standard I consider for the specimen, the tensile specimen, that is the flat plate actually. with some gauge length and thickness and those all things. If you want to do a practice, then you can follow those standards. And again, this is the summary actually. We have the material parameters and damage evolution parameter. These are the value of the damage evolution parameter. Fracture strain play important role and the plastic strain play important role. In the next video, we will discuss about those 2 points. And once you know the fracture strain and plastic strain means material property, you need to calculate the displacement at failure, and we want to define the linear softening behavior. So how you can define? We simply need to calculate the length of the element, or we can say characteristic length of the element. We must need to know that is nothing but minimum of all edges and median for the plane stress plane strain condition. In the 3D, that characteristic length will be, calculation of the characteristic length will be different. So at the first point 0, 0, we not need to define in the linear form as I explained in the previous slide. In the second point, the damage will be 1. Again, it not need to define here. Only we need to define the U value, displacement at failure value, and that we can calculate as the characteristic length of the element into the plastic strain, ultimate plastic strain. So here I define only 2 parameters for sake of simplicity. So my final plastic strain is 0.05, means this graph will be moved likewise from this point to this point, then a straight line again from this point to this point, and this point is my nothing but strain is 0.05 and stress will be 110. So we nothing to do with stress, we need only the strain. So the ultimate strain is 0.05 and the characteristic length of these element around 4. So 4 into 0.05, that will be around 0.2. So we can feed this value as 0.2. Here value is 0.158. Why? Because the length of the element is little bit lesser. So that's all this video. Next video we will talk little bit more about the same parameters, like how the plastic strain and the fracture strain affect the simulation. Even we define the damage evolution parameter and displacement at failure properly, but still element deletion not take place. The reason may be the fracture strain, boundary conditions and our plastic strain. So we will talk on that in next video. So thank you very much. If you have any question or query, you can make a comment in the comment section. And if you willing to learn and share knowledge, you are most welcome to join our Facebook and Telegram community. Links are available in the description. Thank you again.